Welcome to the Explainer. Okay, let's just jump right in. Have you ever wondered how we actually translate human problem-solving logic into literal electrical hardware commands for a microcontroller? Like, how does a thought become an action? Today, we're going to bridge that gap. We are exploring how to take an abstract idea floating around in your head and turn it into precise C programming code that commands a physical chip to do exactly what you want it to do.
Here is our roadmap for today. First, thinking like a computer. Second, mapping the flowchart. Third, C basics and variables. Fourth, bits, bytes, and ports. Fifth, mastering program loops. And finally, building blocks with functions.
All right, starting off with Section 1, Thinking like a Computer, which is all about algorithms and pseudocode. So before we can write a single line of C code, we really have to train our brains to think sequentially. And an algorithm totally demystifies this process. It's essentially your ultimate recipe or roadmap. It's an exact list of instructions that conduct specified actions step by step. You take an initial input, process those instructions to perform a specific computation, and boom, you produce an output. You can use algorithms for something super basic, like sorting numbers, or for incredibly complex stuff, like the system recommending content on your favorite social media feed. They are literally the backbone of all hardware and software routines.
And this right here perfectly illustrates pseudocode. Pseudocode is basically an algorithm written out in plain, informative English. It has absolutely zero programming syntax, so, a computer can't actually compile it. But that's okay, because its job is to help us structure our thoughts. Take this sequence for adding two numbers in a PIC microcontroller. First, input the numbers. Second, move the first number to a working register and the second to a general-purpose register. Next, add them together, and finally save the result. See? It perfectly outlines the logic before we even touch real C syntax.
Moving right along to Section 2, Mapping the flowchart, so we can actually visualize this logic.
Let's translate that text-based pseudocode we just talked about into a highly visual diagram. A flowchart maps out a workflow, and what is so fantastic about them is that they use a strictly defined set of standard symbols. Because these symbols are universal, literally anyone looking at your diagram can instantly understand the program's execution path. It's the ultimate visual representation of your algorithm.
Let's go over the basic vocabulary of these shapes. On the left, we've got the oval terminator. This symbol marks the absolute beginning or the absolute end of a program. You'll usually just see it holding the words start or end. Over on the right is the rhombus, and that represents a decision. Think of this as a crossroads. It dictates which path a program should take based on a specific condition, which is a lot like an if-then statement in your code.
We also use the standard rectangle to represent a core process. This tells us a specific action or calculation is taking place. Meanwhile, that tilted rhomboid shape is used for data. It flags incoming inputs to the system or outgoing outputs, which is very similar to assigning a value to a variable.
Section 3, C basics and variables. Let's learn how to speak the microcontroller's language.
With our visual map all drawn out, let's zoom in further to actual programming with C, starting with the core vocabulary. Listen, compilers have strict rules. The micro-C compiler, for instance, recognizes exactly 33 reserved keywords. We're talking words like int, void, return, and while. Because the compiler uses these words for its own structural logic, you absolutely cannot use them as your own custom names for variables or functions. No exceptions. Also, keep in mind that the compiler is entirely case-sensitive. It definitely cares about uppercase versus lowercase. And while your custom names can include letters, numbers, and underscores, they can never, ever start with a digit.
Speaking of your own custom names, you have to declare every single variable before using it for the first time. Why? Because variables are physically stored in your microcontroller's RAM memory, and you have to reserve that byte space beforehand. Fortunately, C lets us be super efficient about it. You can declare the type, the name, and the initial value all in one single step. For example, setting an unsigned integer named gate1 to an initial value of 20. It's quick, it's clean, and it gets the job done.
Okay, Section 4, Bits, Bytes, and Ports. This is where we actually control the hardware.
This right here is where software meets the physical world. Let's see how our C variables manipulate actual physical pins. To talk to the hardware, the C compiler relies on specific prefixes so it knows exactly how to read a number. A number with no prefix, that's just your standard decimal. But if you slap a 0b on the front, you're telling the compiler it's a binary number. A single 0 prefix means it's an octal number. And arguably the most common one you'll see for hardware control is the 0x prefix, which stands for hexadecimal. Notice how the decimal decimal 255 translates perfectly to 0FF in hex or a full byte of ones in binary.
Using these values, we can explicitly command the hardware bits. It's like having microscopic fingertips. For example, writing trisc.f0 equals 1 sets the 0th bit of port C as an input. Or let's say we want to blast all the pins on port B to logic high. We just set port B to our hex value 0FX. You can even use standard decimal, like setting port D to 128, which flips that 7th bit to logic high. You are literally turning tiny electrical switches on and off using nothing but lines of text. How cool is that?
Moving into Section 5, Mastering Program Loops, because we definitely want to automate repeating operations.
Microcontrollers are basically the ultimate employees for repetitive, tedious tasks. Let's look at how we trap the processor in a productive loop. First up is the classic while loop. A standard while loop repeatedly runs the commands enclosed in its curly brackets until its checking expression becomes false. Simple enough, right? But check out the endless loop on the right, while 1. Because the number 1 always equals 1, the condition never ever becomes false. This is the microcontroller's Groundhog Day. It gets trapped running that task forever. And honestly, this is absolutely essential for embedded systems that need to continuously monitor sensors without ever shutting down.
Now, if you want a loop with a bit more built-in structure, the for loop efficiently packs everything into one neat little package, right at the declaration. It requires 3 distinct parts: the initial starting value, the stopping condition, and how the value changes after each iteration. So if you want a process to happen exactly 5 times, you set k to 1, tell it to run while k is less than 5, and tell it to increase k by 1 after every single cycle, which is exactly what that k++ syntax means. But what if you have a scenario where you absolutely must execute an operation at least once before you even bother checking the condition? Well, for that, you'd use a do-while loop. Notice how the while condition is pushed to the very end of the statement. In this specific example, the code will add 1 to the variable a and then check if a is less than or equal to 1,000,000. It guarantees the action happens first, keeping the program looping until exactly 1,000,000 iterations are reached.
Finally, we've arrived at Section 6, Building Blocks with Functions, to help structure your code.
As your code grows more complex, you really can't just have one giant, endless list of commands. It gets messy fast. You need to organize it into specialized, reusable building blocks, which we call functions. A function usually has a name, a body of commands, parameters, and a specific result type. If a function is defined as void, simply executes its internal commands and returns no result back to the system. But for functions designed to actually calculate data, they use the return command to pass a specific calculated value right back to the main program for further use.
But here is the major catch, and it's a crucial point. No matter how many amazing custom functions you build for your device, every single C program must contain one specifically named main. Why? Because the compiler demands a starting line. Execution of your software will always start with the main function, even if it's not the very first thing written at the top of your document. Let's look at creating a custom function, like this one here, which computes the physical volume of a cylinder. At the top of our program, we declare a prototype with formal parameters, r for radius and h for height. Inside the body, it multiplies pi by the radius squared times the height and returns the resulting volume, v. Later in your program, when you actually need to calculate the volume of a real-world tank, you just call the function. The compiler seamlessly swaps your formal parameters r and h with your real parameters, radius and height. It does the heavy lifting for you. So, we have covered a ton of ground today. From mapping out sequential algorithms using plain English pseudocode and visual flowcharts, to zooming all the way into the exact C syntax of loops, variable declarations, and actual hardware port controls. Armed with all this knowledge of how to manipulate physical pins with nothing but code, what are you going to program your microcontroller to do? Thanks for joining me on this explainer, and happy coding!